Hey everyone, I'm Ben. I'm a PhD student in the physics department. I work with Susan Clark, and today I'm going to tell you about scalable Gaussian processes with Vecchia's approximation. So a bit of scientific context. This is an image of the Milky Way, our galaxy, and all those beautiful dark splotches you see, that's caused by little grains of carbon and silicon that we call interstellar dust. And it's a big project in the field to figure out what the 3D structure of this dust is. We can't at all measure that directly, so we use indirect line-of-sight integral constraints, which turns it into kind of this big, ill-posed inverse problem. And I put two recent works that are tackling this from different directions. The one on the left uses a 3D Gaussian process prior. So any two dust voxels are correlated a priori depending on how far they are away in space. And on the right is another work that uses more exact inference and covers a much larger volume, but doesn't use that kind of prior, and you end up getting these unphysical kind of streak artifacts. So a big motivation for us is to be able to represent these Gaussian process priors on a much larger scale. So how do we do that? We use something called Vecchia's approximation. Basic idea is when you have a voxel, you'd like to correlate it with your entire map that you've generated so far, but if you do it in the right order, you can get away with only correlating with the nearest neighbors. And this is not the same as truncating the covariance matrix there. Correlation can still propagate over long range through the conditionals. The way to think about it is the precision or inverse covariance is sparse. This is a technique that's been applied in spatial statistics at the 100,000 to million parameter range, but we need to push this to near a billion or beyond parameters for our application. So our main contributions, algorithmically, we change up the order a little bit to match a KD tree order that lets us do our particular neighbor searches really fast. And we also modify that order a bit as well to make our dependency graphs really shallow. That basically allows us to generate big portions of our map in parallel on a GPU, for instance. We really want to use the technologies of AI. In that vein, we implement this in JAX, so we can get derivatives of our model. But JAX doesn't let you do all the performance optimizations you'd like. So we have a CUDA implementation that's more than an order of magnitude faster and uses less than a tenth the amount of memory. But critically, when we have that kind of high performance software, we also implement the derivatives of it and plug it back into the JAX. So you can use it with the whole JAX ecosystem like it was any other JAX function. And the plots basically say this scales super well. So yeah, I'll basically leave it at that. You can scan, there's more details on the GitHub page for this. I'm excited to use this for 3D mapping in the Milky Way, but I think there's a lot of other great potential applications. So I'd always be happy to chat. Thanks.